Okay, recording is in progress, guys. Welcome to our class today, Wednesday, January 26, 2022. Today we'll continue in handout 2, and we'll have some class notes. I just uploaded the class notes 3, 4, and 5, which will be covered maybe tomorrow and next week classes. Last week we stopped at the end of deterministic finite automator, the 6 examples, and today we're going to continue with the class note. But at the beginning there was a class exercise or a question. So who would be the volunteer to answer the question? Okay, Austin Jang.
Yeah.
I'll allow you to share your screen to show your colleagues the question and to start answer.
Okay, sorry, 1 second. Yeah, so the answer yesterday, so before I share my screen, so the thing's loading right now. So the answer to the question that happened last week was basically.
Can you share your screen so your colleagues know which question you are talking about?
Yeah, of course. Here it is. So this is the question that was asked last week.
Yeah.
Yeah, so the note is a little bit, can you guys see the white sort of strokes on here? Okay, perfect. So basically, this state transfer between the double E and double O to EO or OE is basically both 1 and 0 would transfer to there. So I made an example of 1, 1, 0, 0. Basically, it's a double E scenario. If you add a 1, it's going to be 3 1s and 2 0s. And if you add a 0, it's going to be 3 0s and 2 1s. So both will work. So the other way around will also work. So with, say, like a 3 1 scenario, you could add a 1 and make it 4 1s, and so that becomes the EE as well. And then if you have like a 3 0, you can add a 0 and make it a number of 0 as well. So that's basically how the state transfer works. Hello? I think you're muted, sir.
Yeah. Okay, guys, the questions. Okay, just let me record that you answer this question, Austin. Come on, just a sec.
Cool.
Okay, recorded and saved. Okay, so I'll share my screen right now. Can you see my screen, guys?
Yes.
Okay. So we talk about DFA or deterministic finite automata in last Thursday class. So just as a class notes definition and notations, what do we mean by those? It's like a quick revision. It is an alphabet is a finite set of symbols denoted by sigma or rho, this symbol, but we use sigma in our course and in our textbook. A string over an alphabet is a sequence of symbols from that alphabet. For example, if our sigma is 0 and 1, then W is a string that consists of 0, 1, 1, 0, 1. So length of a string is the number of symbols in the string denoted by the cardinality of that string, cardinality of W, which is 5. The empty string is a string consisting of 0 symbol denoted by epsilon. Sigma I, which equal a string where W is a string over sigma and the length of W equal I. When I say sigma 5, that's a string that consists of 5 symbols. Sigma 4, that consists of 4 symbols of that alphabet. For example, if my sigma is 0 and 1, and I said sigma square, that means any string consists of 2 symbols of that alphabet or any combination of 2 symbols of that alphabet, which is 0, 0, 0, 1, 1, 0, and 1, 1. Clean star or sigma star, it is the set of all possible strings that can be constructed over the alphabet sigma, which is equal to the union of any combination of the length of that string started of 0 and more of that alphabet. Sigma 0 equals 0, which means the empty string epsilon. So a language L over an alphabet sigma is a subset of clean star or sigma star. Back to DFA. Let's have this example. Assume that we have a language L. L consists of string W. W ends with a 1. If you receive this question in the exam and I ask you construct a DFA that accepts all strings are in this language. So as we talked before, the first thing that we have to identify the number of states I need. So the state that end with a 1 should be the final state. Start state, whatever, I receive a 1 or a 0, I will continue. So here we need 2 states, state that deal with zeros and a state that deal with 1, which will be the final state. So I start with Q0. If I receive a 0, I will stay on that state. If I receive a 1, I'll go to Q1. If then I receive a 0, I'll back. And if I receive 1, I will stay on that state, which is the final state of that alphabet. Definition. A DFA, a deterministic finite automata, is a 5-tuple. It's the same as in the handout, which is a Q, sigma, delta, Q naught, and F, where Q is a finite set of state, sigma is the alphabet, delta is the map between the input Q of the state that taken from the alphabet, and it will send me back to that Q, a set of states, is the transition function, we call it. Q naught is the start state, and F is a part or equal to Q is the set of accept states. We say that a DFA, M, Q, sigma, delta, Q naught, F accept the string W if starting at state Q naught, the DFA ends at an accept state on reading the string W. So we will say that the language M will accept, or the language L, whatever you call it, that will accept the string W or S or whatever you call the string. The DFA M accept the language L that included or equal to sigma star if every string in L is accepted by M and no more, denoted as L of M, a language of the DFA, we call it M. This is also referred to as M recognizes L. So these are some class notes and some like formal and informal definitions that might help you to understand the handout. Question till this point. Guys, do start forming the groups for the final assignment or third assignment. If not, please do it as quick as you can. Because soon as after handout 3, we will release assignment 1. Okay? Okay. Now we talk about deterministic finite automata. Now we'll talk about non-deterministic finite automata or non-determinism. Determinism versus non-determinism. What's the difference? Why? Given current state Qi belong to Q and next input symbol X belong to alphabet, the transition function delta of a DFA defines exactly one state, Qj, that belongs to Q, to move to it. We call this determinism. So once we receive an input, we know the next state. This is what do we mean by determinism. The next state is determined by the current state and next input symbol. Once I have the current state, the next input symbol, then I know the next state. In graphical terms, this means exactly one arrow comes out of every state for each letter in the alphabet. If I receive a 0, where to go? If I receive 1, where to go? This is what we call it determinism. There is one state I'll be moved from the current state once I receive certain symbol from that alphabet. The non-determinism, it is challenging. How? The idea that there must be a single path to a computation. What if many paths of computation could be followed at the same time? I can go here or there, or here and there, and they go in parallel. In that sense, non-determinism can be viewed as a kind of parallel computation in which many threads can run concurrently if at least one such thread accepts the computation accept. So here I have multiple paths. If I end up with one of these paths and with accept state, then we will accept. Then we will accept. So what is the non-deterministic finite automata? A non-deterministic finite automata, and we call it NFA, is like a DFA except. What are the differences? One or more transitions are allowed for each symbol. In deterministic, with the symbol and current state, there is only one state would accept the computation path. In this one or more, I can go on different path. Transition can be made without reading any symbol. Here also, there is another difference with epsilon. Also, I can move to next state. The machine accepts if any sequence of choices lead to an accept state. I might have four paths. These paths, there is one of them or more lead me to accept state, then I will accept. So Also, a non-deterministic finite automata or NFA is a 5-tuple, Q, sigma, delta, Q naught, and F, where Q is a finite set of states, alpha a finite alpha bit, delta Q times alpha epsilon, and it will send me to the P of Q, a transition function, Q naught belong to Q, and F, which is the final state, also included in Q, a set of accepting states. I might have multiple accepting states, depending on different paths. The main differences in FA relative to DFA pertain to the alpha bit and the transition function delta. Sigma epsilon equals sigma union epsilon. Recall P of Q, which is the power set of Q. You remember in the first class we took the power set. Remember what is the power set. In other words, the transition function take a state and symbol or the empty string epsilon and produce a set of possible next states. Example, given an NFA that accepts a string that end with 0, 1. Here we assume that alphabet is sigma equals 0 and 1, 2 symbols. And here they said to us that this any string that end in 0, 1. So any 0, 1 I received here. So if I receive a 0, I could go to the next one if it's the last symbol. And if it's not, I'll stay in this one. So with the 0, I have this path which lead to the same state, and also I have another path that lead to Q1. And if I receive 1, I will end at Q naught, which is the Q2, which is the accept. So formally, A, Q naught, Q1, Q2, and sigma is 0, 1. Then delta, which is the transition function, we start at the Q naught and we end at the Q2, where delta, which is the transition function, is if I'm at Q naught and I receive 0, I could go to Q naught or Q1. In deterministic, we go to only one state. Then, if we receive 1, we stay at Q naught. Here, if I'm at Q1 and receive a 0, I'll do nothing. If I'm at Q2, if I'm at the last 2 symbol and I receive 0, I'll do nothing. If I receive 1, I will end at Q naught, and this is the accepting state. So if you see the transition function, it's different than the deterministic finite automata. Look at the NFA computation path given to the input string 0, 0, 1, 0, 1. So I'm at Q naught. I receive a 0. I go to Q1, 0. Then I'll go to the dead path. Here, what we mean by parallel. Then if I move, if I use that, the one that I back to here, I'm at Q0. I'll stay at Q0. Then I receive a 0, I'll go to Q1, then I receive a 1, I'll be at the Q2, then there's a still 0, 1, then I'll go to the dead state. Here, if I receive a Q0 and stay at Q0, then I receive a 0, stay, then I receive a 1, I stay at Q0, then I receive a 0 at Q0, Q0, then the state. And here, this path will take me 0, 0, 1, I'll stay at Q0, then I'll move to Q1 and Q2, which is the accepting path. So here I have multiple paths. 3 of them will lead to the state and 1 will lead to accept the state. Then I will accept that string. So since we need at least one thread accept and in me at the final state, then all the computation accepts. Okay, given an FA that accepts all string that contains string 11010, and the dimension it's at the left side end or in between, that contains wherever it contains. So here we'll do the Q naught 0 or 1, I'll stay. then 1 1 0 1 0 and end, or whatever I received here. So it will give me either it's be at the right side of the string, which is end with or started with, and whatever I received between or in between. With this NFA, I put in my under consideration all the possible path wherever the 1101 0 located in that string. Question: what is the role or purpose of the loop transition in Q note and Q5? I answered this question. This would help me that if this string are in the middle, it would help at the left side, at the beginning of the string or at the end of the string. It would help me whatever is the situation. How would the language machine recognize change if you omitted either of them? This is a question to be answered by a volunteer next class. Slide 29. Recorded. How would the language, the machine recognize change? Stay here or to move to that one you omitted either from. NFA, example 2, continued. Recall the equivalent DFA. If we said deterministic finite automata, we will make it here for zeros. If we receive a 1, we'll go to Q1. If we receive a 1, which is the string, otherwise we will have some back arrow to resend me back to reread the symbol. So notice the NFA was much easier to write and read. So normally NFA are easier to be constructed and to be read. Okay, in fact, giving any string S consists of symbols A1, A2, A3 to AN and alphabet sigma. The NFA that accepts all string containing S is start AI, which belongs to sigma, then A1, then A2, then A3 to AN, AI of the sigma, whatever is repeated, and it will be at accept state. This is a very generic level of constructing a DFA. Epsilon transition. You remember here at the beginning we said that the deterministic called epsilon transition. What do we mean by epsilon transition? It is an non-deterministic finite automata can make a transition without receiving any input. These transitions called epsilon transitions can sometimes greatly simplify the design. So it moved me from one state to another state, even if I did not receive an input. This is a very important thing that will simplify my job in constructing an NFA. So using epsilon transition, give an NFA that recognize the set of string that end in I, in NG or ER for alphabet that consists from A capital to Z capital. So here I have two things and two accepting state, either end of ER or end of ING. So I have two paths. How I'll move to each path? I'll move with epsilon transition. Without an input, I'll go here. It will keep AZ. Once I receive I, I'll move here, then to I, to N or J, G, or also I'll move here. Then if it ends with ER, then I will end with accepting state. So non-determinism, two interpretation. Why I do need this in computation? This is a question you might ask. Why I'm studying this? Why we design this in programming languages or in any computation system? There are two equivalent ways of thinking about non-determinism. The first one is parallel computation, and the second thing, which is lucky guess. What do we mean by parallel computation? that I have different computational threads that running at the same time. I should end at one of these paths in accepting state, or more, at least one or more, then I will accept that language. So the computation proceed along all possible paths concurrently at the same time. The second one, lucky guess, the computation proceed along one path only, but always picks the path that leads to an accepting state if such a path exists. You know, you can you use in many math problem, you use random number, right? Which is a guess by a computer, this number. So there is a guess that the computer guess this is the correct path, then it will try it. And we call it lucky guess. Clear, guys? Clear? So let's see some class note about those. Example of DFA. So assume that we have a language L1 that had a string W, which belongs to the alphabet to any combination of zeros and one. W has an even number of ones. Okay, there is a condition here. There is a constraint that I should have an even number of ones. So I'll start at Q node. If I receive 0, I'll stay here. If I receive a 1, then I end by 1, then I will end at accepting state. But if I receive another 1 to be an odd number, then I'll go to the state. Is that clear? So the starting state, it's the final state in order to have an even number of ones. Q naught, all string having an even number of 1. Q1, all string having an odd number of ones. Because assume if I have 2 ones, 1, 2, done, accept. If I have 3 ones, 1, 2, 3, whatever zeros in between. So I will end at Q1, which is a dead state. So question 2, if I have L2, which consists of AB, 2 letters, AB, and end with the substring AB, it should be end by AB. Then I'll start at Q node. Whatever, if I receive B's at the beginning, I will stay at Q node. Once I receive an A, I'll stay at Q1. Then whatever I receive A's, then B, I'll end at final state because at that time it's end at AB. If I receive an A again, then I will keep going till I receive B. And then if I receive a B, I receive A, B, B, for example, I'll back to Q naught. So all string that end with A, B, Q2, Q1, all string that end with an A, Q naught, all string other than Q naught or Q1, remaining strings that end with AA, BA, BB, you will stay here. Okay, another example. If I have language tree that has W as a string over an alphabet 0 and 1s, W is divisible by 3. Okay, divisible by 3. When the number is divisible by 3, which means that W mod 3 equals 0. What are the options? When I divide any number by 3, either the remaining is 0 or 1 or 2, right? Because if it's a 3, then it's 1. 3 over 3 is 1. So a mod answers if the mod is 0, that means it's divisible by 3. If the mod is 1, it's not. If the mod is 3, it's not also. So then I'll have 3 states. I need 3 states, Q0, Q1, and the Q2. So at Q0, if I receive a 0, I will stay at the beginning. Then if I receive a 1, I'll move to Q1. If I receive a 0 again, I'll back to Q2. And in a Q1, if I receive a 0, I'll go to Q2, 0 back to Q1, and 1's here in between. So this is for any number to be divisible by 3. So another volunteer for next class to show us examples how this NFA works for this question. So we have now next class 2 volunteers till the moment, which is tomorrow. Okay, if I have language 4 that has a string W that belong to 0, 1, W begin and ends with the same symbol. It's either begin with a 0 and end with a 0, or begin with a 1 and end with the 1. How many states do I need? Q0, which is epsilon. Q1 for those who begin with a 0 and end with a 0. Q3, which begin with a 0 and end with 1. Q4, which begin with a 1 and end with a 0. And the Q2, which begin with a 1 and end with a 1. So let's see. We have here Q0. If it's start with 0, if it's received 0, I will stay in a 0. If it's received in a 1, I'll keep in a 1. And then if it's received a 0, I'll back to here and in that final state. If we started with 1, we'll do the same. If we receive a 0, we'll go to 4 and stay. Then if it has a 1, we'll back to 1 and end on this 1. So I have 2 final state. One, if it's begin with a 0 and end of the 0, and the other path, if it start with a 1 and end with a 1. Notes. For a language, there can be many DFA accepting it. In fact, there can be infinite many DFAs, but every DFA accepts exactly one language. Given a set of Q and A, Q is a state and the symbol, then I end with a Q prime, which is the state, and it's a unique state that will lead me to that state. If I receive that, why we have the word deterministic. This is for deterministic. The set of state in a DFA partitions the set of all strings. Set of state is finite. Is for regular operations, same as in A1 to AN, the example that we took in the handout. We say that M accept W. If this symbol, that means there is exist. There is exist. If there is exist a sequence of state, R0, R1, R2 to Rn, such that R0 Q0 initial condition, R1, which is the transition condition, Rn, which is the final or accepting condition. Note that the states Ri need not to be distinct. Let L be a language where L belong to or included in sigma star. We say that M accept L if there is a language L with a string W that belong to that alphabet, M accept W. Let L be a language L included in that alphabet. We say that L is regular if there exists a DFA M such that L equal L of M. We will stop here now because this example, we'll talk about it with next handout. So later will be proved after DFA. So, but to let you understand the example, if I have a language that consists of 0 to the power n, 1 to the power n greater is the 0, is not regular language. How we will prove this? we will talk about something that we call it pumping a lemma with regular languages. That will be talk about, I think, handout 3 or 4. Here, another example that if we have a language L1 with W that does not contain 1 as a substring. So if we have 1, we'll go to data state. If we have only 1 as a substring, then zeros, then it would be accepted. But 1, that will lead me to a data state. Questions? So here we'll talk about equivalence of deterministic finite automata and non-deterministic finite automata and closure properties of regular languages. So guys, we'll give you like 5 minutes break to start with this handout because I need your full concentration. So I'll see you at 11:17. Welcome back after the break. It's 11:17 now. Okay, guys, just as a reminder that the group sheet should be ready by February 1st, which is next Tuesday. On Wednesday or that week, before the end of that week, the final group list will be announced. Okay, for those who put their name as individual, one of them, he just wrote his email without his name or her name, I don't know. So please fill in your name properly and the formal name in the university. Don't use the nickname. Please use the formal name as in the class sheet or the class list. Okay, so let me share my screen again. Can you see my screen? Yes, okay, good. Okay, so equivalence of DFAs and NFAs, closure properties of regular languages. Equivalence of NFAs and DFAs. A natural question to ask of how DFAs and NFAs are related. On first glance, it seems like NFAs can do more. But is this really the case? The first step to answer this question is to ask, given a DFA, does there exist an equivalent NFA? What do we mean by equivalent? We mean that they accept the same language. Theorem number 1, all DFAs have an equivalent NFA. Every deterministic finite automaton has an equivalent non-deterministic finite automaton. This is the first theorem. Proof. The proof is by definition. Every DFA is also an NFA. It just so happens that DFAs do not make use of extra power of the NFA, which is the multiple transition or the multiple paths and the epsilon transition. It is the same as NFA without the multiple transition property and the epsilon transition. So each DFA is an NFA. Clear? Now we'll go one more step. So now it's become harder. Prove that every NFA has an equivalent DFA or not. If every NFA has an equivalent DFA, then NFA ultimately have no more computational power than DFAs. We prove that each DFA has an equivalent NFA, or DFA is an NFA without using the two properties, which is the epsilon transition and the multiple transition. But if we go the other way, all NFAs have an equivalent DFA. Every non-deterministic finite automaton has an equivalent deterministic finite automaton. To show every NFA has equivalent DFA, it would be sufficient to prove the existence of a general algorithm to convert, this is I think a typo, to convert any NFA into an equivalent DFA. How to convert? We begin by reviewing each component of the definition of a DFA to see what need to be adjusted. States. The first thing we have to consider is the finite set of states in an NFA. The computation can be in combination of states at the same time. In a DFA, it can only be in one state at any time. Idea, let sets of states in an NFA each be a single state in the corresponding DFA. Continuing in states, example, suppose an NFA transition to states Q0 and Q1. In our corresponding DFA, we can define a unified set of state Q0 and Q1. How many such states do we need? If our NFA has a Qn equal k states, our DFA QD power of the Qn, which is 2 to the cardinality of the Qn. Example, Qn equal Q0, Q1, Q2, then Qd equal phi, Q0, Q1, Q2, Q0, Q1, Q0, Q2, Q1, Q2, Q0, Q1, Q2, where phi is the state, which we will omit for national clarity or notational clarity. This is complete set of state that our DFA could possibly use. Of course, as we fill in the transition table, we may find some or even most state not go unused. The alphabet, that sigma n equals sigma d, starting state let Q0 belong to Qn, B the starting state for our NFA, the starting state for the corresponding DFA is a Q0, union the transition of a Q0 and epsilon. Combination of a Q0 and any other state reachable from a Q0 by an epsilon transition. The final state, so the Fn, it would be the same or any computation like for Q1, Q1, Q0, Q1, Q2, Q0, Q1, Q2. The transition function, filling the transition function, delta D proceeds in two parts. Part one, we write table with single state for rows and letters for columns. We use NFA as a transition function delta n to fill in this table, converting set of states to the unified state or amalgamated states, they call it, but you can use the union state, but we still have to count for the epsilon transition. The way we do this is as follows. If the transition from a state Qi to state Qj and the Qj consists or contains an epsilon transition to state Qk, then in effect Qi transition to Qj union Qk. to overcome the epsilon transition. This continues recursively until there are no new epsilon transition to follow. Then we will add new rows to the table corresponding to the unified state or union states or amalgamated states, which are Q0, Q1, Q0, Q2. We will fill these cells by taking the union of the cells of the corresponding single set or states. Example, to fill in the delta D Q0 Q1 with A, we will take a QD Q0 A and Q1A. For example, convert the following NFA to an equivalent DFA. We start at, this is a Q0, or we call it 1. If we receive epsilon, we go to 3. If we receive a B, we'll go to 2. If we receive A's, we'll stay here. If we receive either A or B, we'll go to 3. If we receive A, we'll back to 1. So how we'll do this? These are the steps as explained before. Here we'll have A and B, and if we are here at 1, if we receive A with epsilon, what we will do, if we receive 2 and 3, all these combinations, then we'll continue to fill in the table with combination or single states. Then we'll try to use the minimization problem so we can eliminate these states or unused states. And we will end by, if we put it together, we'll have a DFA that's look like this. And here we'll back to the first statement. We said that NFA is simpler and easier to read than the DFA. So DFA is more complicated or more complex. So if you see in NFA, we have this simple diagram or a finite tomato diagram. But if we make it back to DFA, we will end at this one, and some of them will contain different state. And this is after elimination. This is after elimination. If we don't eliminate it, we'll have more states. So to continue with equivalence of DFAs and NFAs, what does all this mean? We recall that we proved by definition that all DFAs have an equivalent NFA. Then we demonstrated an algorithm showing all NFAs can be converted into an equivalent DFA. NFAs have no more computational power than DFA. In fact, the set of languages recognized by DFAs and NFAs are equivalent, and we call them the regular languages, as we explained in the previous lectures. We define the regular language. Is that clear, guys? Tomorrow, we'll not have a handout. We will go with class note 4 with the regular operations. And what do we mean by non-determinism? We will revise this and how we will do these things by definition. Then in 5, what is the exact differences between DFAs and NFAs? The formal definition of NFAs again. What do we mean by those? We'll take some examples. And we'll have some conditions, equivalence of NFA and DFA, our topic today. We will have more explanation with examples on those and how we prove those, how we prove it in terms of figures. And we will end our class tomorrow. So, any questions? As I told you guys, that the material of this course is a bit abstract, a bit rigid. However, with more example, with more practices, we will start get used to it, and it would be like of simple things for us. If you don't have a question, you can leave. Don't forget the 2 volunteers at the beginning of the class tomorrow. If you have a question, you can stay, and I'm ready to answer. Thank you, Andrew. Thank you, Mahira. Brandon, have a good one. Thank you, Abdullah. Robert, thank you. Questions, guys? Or shall I end the meeting and stop recording? Okay, see you tomorrow, guys. Have a good day.